All right. Life is really about keeping things balanced because nature likes balance. Nature likes things to be even. And that's definitely the case when it comes to balancing reactions. So when we look at a formula equation, it shows the number of atoms of each element involved in a reaction. So I've got one iron atom reacting with two oxygen atoms forming two iron, three oxygen. Okay, so we've got this, but there's a problem. And the problem is I somehow created an iron atom and I somehow created an oxygen atom. That's problematic. Okay, so we need to deal with that. And so the way we deal with that is called balancing a reaction. So we can't simply make atoms, and so we need to somehow change the quantities to make this work out. All right, so the first thing we got to do, and once again, there are different methods for doing this. The way I learned it in high school was essentially trial and error. You put numbers in places until you got all the atoms to work out, and it's a real pain in the butt. This method, until you get comfortable with balancing reactions, works really well. And so we need to first count how many atoms we have of things. And so it's just a skill that you need to have. So looking at this formula, BaCl2, that 2 only applies to the chlorine. So I have 1 barium and 2 chlorines. Lithium sulfate. Okay, so I've got 2 lithiums, 1 sulfur, 4 oxygens. That 4 is only on the oxygen. Okay. Then iron carbonate. This is iron 3 carbonate. I have 2 irons. Remember, the 3 out here applies to everything in the parentheses. So I have 3 carbons and 9 oxygens. Okay? Because this 3 multiplies everything inside. So 3 times 1 carbon gives me 3 carbons. 3 times 3 oxygens is going to give me 9 oxygens. All right. So the first step in any balancing is we're going to count the elements on both sides. It is critically important, not just important, critically important that you count them in the same order on both sides. Otherwise, you're going to be asking for confusion, and we don't want that. Okay? So simply looking at the left side of the reaction, I mean, these are like, literally, you can just draw, I mean, you can draw a line here if you need to, just to separate these two sides. Okay, so this is the reactant side, this is the product side. They are kind of like separate worlds. They don't interact too much. Okay, we need to make them balanced, but they're not going to interact. Okay, so 2 potassiums, 1 sulfur, 1 barium, 2 bromines. And then on this side, 1 potassium, 1 sulfur, 1 barium, 1 bromine. Okay, so that is the first step. The second step is to add what we call coefficients. And to make this easier to understand where coefficients go, I like to draw dashes here. And so I draw a dash in front of everybody because each of these could get a coefficient. And a coefficient is just a number that we're going to put right here on these dashes, and they are going to multiply whatever they're in front of. So for example, if I put a 5 right here, 5 times would give me 10 potassiums and 5 sulfurs. Now the 5 would only apply to this. It wouldn't affect this, or this, or this. Okay? So we need to add coefficients to try to balance everything out. So if we look at it, I like to generally start, in general, we'll get some other rules in a minute, but I like to start at the top and work my way down. So my potassiums are not balanced. I've got 2 on this side, 1 on this side. So I need to add a coefficient to multiply my potassium to get 2. So what I'm going to do is I'm going to put a 2 right here. By putting a 2 in front, it multiplies the potassium by 2, giving me 2, so that these are now balanced. But it also multiplies the bromines by 2. And now this bromine on this side is also 2, because 2 times 1 is 2. Okay? And so you got to keep in mind that coefficients are going to change everything that they're in front of, not just the one element that you're looking at. Well, in this case, that balances this reaction out. Okay? That I've got 2 potassiums, 1 sulfur, 1 sulfur, 1 barium, 1 barium, 2 bromines, 2 bromines. We would say that this reaction is balanced. Where we do not have coefficients written, they are understood to be 1. So for example, someone could say that this is balance 1, 1, 1, 2. Okay, 1, 1, 1, 2. Okay, that would be another way of writing it out or saying it out, that that's how it balances. Okay, so like I said that right here, it's understood to be 1. The coefficients must be in the lowest whole number ratio. So for example, if you wrote 3, 3, 3, 6, that is technically balanced, because you would have the same number of each element on both sides, but it is also wrong, because it needs to be reduced down to 1, 1, 1, 2. Okay, those are all divisible by 3. And so that's important to see. All right, so we got some different strategies that are going to go along to help us out. So let's look at our first strategy now. So if an element appears more than once on a side, do it last. Okay, of all the strategies, this is the most critical and most important. That's why I'm doing it first. Okay, usually this is going to be oxygen, because oxygen likes to do this. Hydrogen does it sometimes too. But for the most part, it's usually oxygen. So if you look, I've got oxygen here in the carbon dioxide, and I have oxygen here in the water. If I try to balance the oxygens first, it's harder, because I'm trying to balance 3 things instead of just 2. And it just gets really complicated, and it makes everything a headache. So without question, if something shows up more than once on a side, do it last. Okay? So I've got my counting done here. So I've got counting on both sides. I've got 4 carbons, 8 hydrogens, 2 oxygens on this side, 1 carbon, 2 hydrogens, 3 oxygens. Look, 2 oxygens are here in the carbon dioxide, plus 1 oxygen over here in the water, for a total of 3. Okay, what's down here is what's being added, or is the counting. The actual multiplying goes on up here. Don't multiply these numbers down here. That'll get you in trouble. We'll see that in a second. Okay, so let's balance carbon first. Like I said, I like to start at the top. So I've got 4 carbons here. To get 4 carbons there, I'm going to add a 4 right here. So 4 times that carbon is going to give me 4 carbons. Okay, now instead of doing 4 times the 3 down here, because that'd be problematic, that doesn't work. It's counting. So let's look at the right side and count how many oxygens we have now. 4 times 2 is 8, plus the one that's here, 9. So I now have 9 oxygens on the right side. Okay. All right, next I want to balance the hydrogens. So I've got 8 hydrogens over here, and only 2 over here. So I'm going to put a 4 right there. Okay. So 4 times that 2 is going to give me 8 hydrogens. And once again, we need to count. So count the oxygens. 4 times 2 is 8, plus 4 times 1 is 4. So 8 plus 4 gives me 12 oxygens on that right side. Okay. Now I can balance the oxygens. I have 12 over here and only 2 over here. So I can put a 6 right there. Now the oxygens are balanced and I'm done. By saving the oxygens for last, they're easy. But if you try to do them early on, it just creates a huge headache. So save it for last. That's strategy number 1. Strategy number 2. When dealing with polyatomic ions, if they are the same on both sides, meaning the formula doesn't change, it's CO3 and CO3, then you can just treat it as a single element when you're counting, instead of having to count the carbon and oxygen separately. This makes it easier to do. Do be aware, sometimes polyatomic ions are involved in the reaction and change. Like for example, carbonate can oftentimes become carbon dioxide and one of the hydrogens can get kicked off. That's change. And when that happens, you have to do carbon and oxygen separately. But for right now, we can keep them together because they're exactly the same on both sides. CO3 on this side and CO3 on this side. So I just count them as carbonate ions. And then just simply balance it by putting, I need to balance the potassium. So put a 2 to multiply the potassium by 2, which also multiplies the chlorine. and all of a sudden we have a balanced reaction. All right, strategy number 3. This is one that I've never seen in a book, but it works for me, and it works for most people I've given this advice to. It's just one of those things I found through teaching this, is that if you're balancing something and you just cannot get it to work and it is driving you nuts, erase what you've already done. By the way, when you're balancing, do it in pencil. Save yourself the headache. And the correction tape. And so put a 2 in front of the first one and try again after you've erased everything. Because if you try to balance this one, it's difficult because you've got hydrogen shows up in 2 places. The oxygens are already in balance. Really, the hydrogens are the only thing that are out of balance, but they're really hard to balance because they show up in so many different places. So we need to do something different. So by putting a 2 in front of the first one, all of a sudden it give me 2 potassiums. So I put a 2 in front of this potassium to balance it out. And that puts this, changes the oxygen to 2. And then I have 2 hydrogens plus 2 hydrogens for a total of 4. Remember, I'm counting down here. So these 2 hydrogens plus these 2 give me 4. And then I just simply need to put a 2 in front of the water to finish it out. Okay, so what is a headache if you try to do it without that becomes fairly quick and easy if you put the 2 in front. So that is kind of a common way of doing it, and it makes things significantly easier. All right, strategy number 4. It's possible that a reaction is already balanced. In that case, you just simply write already balanced. That's all you got to do. And that makes life a lot easier. Hey, balancing reactions takes practice. Therefore, go to your workbook and practice. Balanced reactions are critical for where we're going. We cannot do conversions or mole conversion, like the stoichiometry stuff that we're going on to in a couple of units, without being able to balance a reaction. It is critical. So work through your workbook, and I'll see you in the next lesson.